Today we're going to go over the second part in our three-part series on the Gram-Schmidt orthogonalization process and orthogonal complements. Let's begin by reviewing the ideas behind an orthonormal basis. Say that V is an n-dimensional vector space over either the real numbers or the complex numbers. We've seen that once we fix a basis beta, our standard representation phi sub beta gives us an isomorphism between our vector space V and the collection of n tuples f to the n. So for this reason, we'll identify V with f to the n from now on. The idea is that we'd like to choose a basis beta that has, quote, nice properties, unquote. Given a basis gamma of V, we're going to construct an algorithm that'll give us a new basis beta, which is nice. By nice, we mean a basis beta that satisfies the following four properties. Let's fix an inner product of V. We'll say that our subset beta is an orthonormal basis if the following four properties hold. First, beta spans V. Second, beta is a linearly independent set. Third, beta is an orthogonal set. That means given any two distinct vectors vi and vj, the inner product of vi with vj is 0 as a scalar. And third, the vectors in beta are normalized. That means each vector vj in beta has norm 1. Recall that the norm of a vector is simply the square root of the inner product of a vector with itself. We discussed a few examples. Let's say that n is equal to 2, and we have the standard inner product. We recall that the standard basis, gamma, can be generated by two vectors, 1, 0, and 0, 1. For any scalars a and b not both 0, we can define two new vectors, v1 and v2, such that the set containing v1, v2 is an orthonormal basis. When a equals 1 and b equals 0, we recover the standard basis, showing that the standard basis is an example of an orthonormal basis for f2. In fact, since essentially a and b can be anything, this shows that there are infinitely many orthonormal bases for f2. Now say that n is equal to 3, and again we have the standard inner product. Again, recall that the standard basis, in terms of e1, e2, and e3, is a basis for f3. Given any three scalars a, b, and c, where a and b are not both 0, we can write down three new vectors v1, v2, and v3 that you see here on your screen. Then the set containing v1, v2, and v3 is an orthonormal basis for v. In the special case where a is 1 and b and c are 0, we recover the standard basis, showing that the standard basis is an example of an orthonormal basis. And, just like before, since a, b, and c can pretty much be anything, we see that there are infinitely many orthonormal bases for f3. Our main goal is to explain how we constructed these bases. Given any basis gamma, we'd like to explain how we can construct an orthogonal basis. To this end, let's say that V is a vector space over either the real numbers or the complex numbers, and let's fix an inner product angle bracket. First, say that W is the span of some linearly independent subset S. We'll define S prime in the following way. First, V sub 1 will just be W sub 1. Next, recursively, V sub I will be W sub I minus some specific linear combination of the V sub j's, where j ranges from 1 to I minus 1. This linear combination will be chosen so that we actually have an orthogonal set. Second, say that W is the span of S prime, some orthogonal set consisting of non-zero vectors. That is, the inner product of vi and vj is 0 as a scalar for I different from j, and each vi is not the 0 vector. Then S prime is a linearly independent set, and moreover, every vector y in the span of S prime can be expressed as a linear combination that you see here on your screen. The whole point here is that orthogonal sets are nice enough so that not only do we know that we have a linear combination in terms of the set S prime, but we can write an explicit formula for the scalars, AI. Finally, say that W is the span of some orthonormal set S prime prime. Remember that orthogonal says that the inner product of VI and VJ is 0 whenever I is not equal to J, whereas orthonormal is an orthogonal set such that each of the vectors is normal. That is, the norm, in our case, of U sub I is equal to 1. Then S prime prime is a basis for W. Moreover, every vector y in this span can be uniquely expressed in the form that you see here on your screen. Again, the idea is that an orthogonal set, or even an orthonormal set, is a very nice basis. And we can not only express every vector y as a linear combination of the elements in this basis, but we can actually express it so that we have nice explicit coefficients. Before we talk about the proof of this, let's discuss some definitions and give some examples. Let's say that V is a vector space over either the real numbers or the complex numbers, and again, we'll fix an inner product, our angle bracket. The act of turning a linearly independent set in terms of some vectors W sub I into an orthogonal set S prime in terms of some vectors V sub I is called the Gram-Schmidt Orthogonalization Process. It's the process in which we're turning a set S into an orthogonal set S prime. If V is a finite dimensional vector space, then we can construct an orthonormal basis, not just an orthogonal basis, with respect to our inner product as follows. First, choose any basis gamma in terms of Wi. Second, we'll construct an orthogonal basis V sub I in terms of the Gram-Schmidt orthogonalization process. That is, V sub 1 will always be defined as W sub 1, and recursively, V sub I will be W sub I minus a certain linear combination in terms of the V sub j's, where j here runs from 1 to I minus 1. And third, we'll construct an orthonormal basis beta by normalizing our vectors. That is, once we've chosen our V sub i's as above, we'll choose U sub I as 1 over the norm of V sub I times the vector V sub I. We'll give some examples of this. First, let's say that V is F2, and let's choose our inner product as the standard inner product. Let's let A and B be any scalars not both 0, and let's consider the two vectors W1 and W2 as you see here on your screen. We know that this set gamma containing W1 and W2 is an orthogonal set of non-zero vectors. Hence, according to the previous proposition, it must be a basis for F2. We're going to use this to construct an orthonormal basis. First, as the Gram-Schmidt orthogonalization process suggests, let's let V1 be W1. We'll choose V sub 2 in the recursive way as W2 minus a certain scalar times V sub 1. However, this scalar involves the inner product of W2 and V1, which it turns out is 0. It's 0 because remember that we've chosen W1 and W2 so that they are orthogonal. So our V sub 2 is just equal to W sub 2. It should make sense that because our basis V1, V2 should be an orthogonal basis, we just recover W1 and W2. Now we compute normalized vectors. We'll let U sub 1 be the normalized version of V1 by taking V1 and dividing it by its norm. And similarly, for U sub 2, we'll let this be V sub 2 divided by its norm to be the vector here you see on your screen. So we've constructed now our desired orthonormal basis beta. Let's consider another example. Say that V is F3, and again, we'll let our angle bracket be the standard inner product. Given any three real numbers A, B, and C, where A and B are not both 0, let's construct three new vectors W1, W2, and W3. The W3 here we've expressed in terms of the cross product. If you don't know what this is, don't worry. We're going to come back and discuss the cross product in more detail as the course goes on. We've chosen W1, W2, and W3 so that they are an orthogonal set of vectors. Hence, according to the previous proposition, they form a basis for our vector space. We'll try our best to construct an orthonormal basis beta. The way that we'll do this, of course, is by first constructing an orthogonal basis in terms of the v sub i's. Then we'll construct a normalized basis in terms of the u sub i's. According to the Gram-Schmidt process, we'll first start with v1 is equal to our first vector, w1. For v sub 2, we'll let this be w2 minus a certain scalar times v sub 1, and the scalar involves the inner product of w2 and v1. However, recall that gamma is an orthogonal set, so this inner product should be 0. That is, v sub 2 is just w sub 2. And finally, v sub 3 should be w sub 3 minus a certain linear combination of the previous two vectors, v sub 1 and v sub 2. In this case, the inner products of w3 and v1, as well as w3 and v2, are 0. Again, this is because our gamma was chosen to be an orthogonal set of vectors. So v sub 3 should be w sub 3. Now, in order to compute our orthonormal basis, we must normalize these vectors. For u sub 1, we normalize the vector v1 to find the vector you see here on your screen. Similarly, for u sub 2, we'll normalize the vector v sub 2. And finally, for u sub 3, we will normalize to find the vector u sub 3. Let's try to write down an example that's a little bit more down to earth. Let's say that v is the span of the following three vectors inside of R4. W1 is 1, 0, 1, 0, W2 is 1, 1, 1, 1, and W3 is 0, 1, 2, 1. We'll choose our angle bracket in this case to be the standard inner product. We'd like to construct an orthonormal basis beta. First, let's compute an orthogonal basis in terms of the following vectors using the Gram-Schmidt process. V sub 1 is just W sub 1. This is always the case in the Gram-Schmidt process. For V sub 2, we define this as W sub 2 minus a certain scalar times V sub 1. By looking at the way that our vectors were chosen, we see that v sub 2 is now the new vector 0, 1, 0, 1. You'll notice that v sub 1 and v sub 2 are indeed orthogonal to each other. If you were to take the standard inner product of these two, you will recover 0. And finally, v sub 3 we can write as w sub 3 minus a certain linear combination of v sub 1 and v sub 2. You see here how we've written out the inner products of w3 and v1, as well as w3 and v2. By subtracting all of these, we now find the new vector minus 1, 0, 1, 0. Indeed, you can check that this new basis in terms of v1, v2, and v3 is an orthogonal basis. Finally, we can construct the desired orthonormal basis by simply normalizing our vectors. We'll define u sub 1 as v1 divided by its norm, u sub 2 as v sub 2 divided by its norm, and u sub 3 as v sub 3 divided by its norm. Let's now return to attempt to prove the proposition. We're going to prove the first statement by induction on the number of vectors in our linearly independent set S. Let's say that S is written in terms of w sub I. We'll now define S prime in terms of v sub I as we did in the Gram-Schmidt process. We're going to prove that S prime is an orthogonal set of non-zero vectors that also spans our set W. First, we can establish the base case. There's really nothing to prove here because v sub 1 equals w sub 1, and so S prime equals S. So let's assume our inductive hypothesis that this proposition is indeed true for some positive integer k0. Now we'll perform the inductive step. As before, let's say that S is the span of some linearly independent set S, and let's define S prime as in the Gram-Schmidt process. Observe that if we denote T sub prime in terms of the v's and t in terms of the w's. Really here, t is just going to look like s, but we ignore the k0 plus 1 vector, wk0 plus 1. T prime actually looks like s, but we're ignoring the k0 plus 1 vector, v sub k0 plus 1. Since t and t prime only involve the first k0 vectors, the inductive hypothesis asserts that t prime is an orthogonal set of non-zero vectors, such that the span of t equals the span of t prime. Now we have to prove three facts about the new set S prime, which is T prime union the K0 plus 1 vector V sub K0 plus 1. First, we'll show that S prime is an orthogonal set. Let's pick two vectors Vi and Vj in S prime, where I does not equal to j. We actually have to show that the inner product of Vi with Vj is 0. But since we have symmetry in the inner product, it really just suffices to show that the inner product of Vj with Vi is 0 whenever I is less than j. We have a couple of cases. If I is not k0 plus 1, then this inner product is 0 by the inductive hypothesis. If j is equal to k0 plus 1, then we just use the definition of V sub k0 plus 1 to see that the inner product is 0. This is why we made this funny choice of sum for our definition of V sub j. Now, we need to prove that S prime consists of non-zero vectors. So let's consider a V sub j in our set S prime. We'll have two cases just like before. If j does not equal to k0 plus 1, then the inductive hypothesis says that V sub j is not the zero vector. However, if j is equal to k0 plus 1, then we just work by contradiction. Let's assume that our vector v sub k0 plus 1 is the zero vector, and we'll find that the vector w sub k0 plus 1 must be a linear combination of the vectors v sub j, which lies in the span of t. However, this actually contradicts the fact that our set S is a linearly independent set, which means that w sub k0 plus 1 is not a linear combination of these previous vectors. So this does indeed show that our vectors v sub j in the set S prime are non-zero vectors. Finally, we'll show that the span of S prime is equal to the span of S. So let's choose a vector v sub j in S prime. As before, we have two cases. First, if j does not equal to k0 plus 1, then we see that v sub j is in T prime, but we also know from our inductive hypothesis that the span of T prime is equal to the span of T, which is contained in the span of S, since of course S is simply T union one more vector. So we do indeed find that if v sub j is in S prime, then v sub j is in the span of S. Now let's say that j is k0 plus 1. Looking at the definition of v sub k0 plus 1, we see that this must also be in the span of S. So this actually shows now that every v sub j in S prime is in the span of S, showing that the span of S prime is contained in the span of S. So now we have to show the converse. So let's assume that w sub j is in S. Again, we have two cases. If j does not equal to k0 plus 1, then we see that w sub j is an element of T, and pretty much the same proof as above, we see that w sub j must be in the span of S prime. If, on the other hand, j is equal to k0 plus 1, then again we just look at the definition of v sub k0 plus 1 to see that w sub k0 plus 1 must be a linear combination of the elements of S prime, and therefore all of our w sub j's are in the span of S prime. This shows the converse, that the span of S is contained in the span of S prime, so we must have equality. This shows that our proposition, P of k0 plus 1, must also be true, thereby completing the proof by induction. Let's now prove the second statement. That is, this is the statement about being a linearly independent set. First, let's consider an expression of the zero vector. Let's say here we have a sum over R elements v sub I in our set S prime. If we take the inner product of this sum with our vector v sub j, then of course the inner product of any vector with the zero vector is zero as a scalar, but also using the fact that we have an orthogonal set, we now see that we actually have an a sub j times the square of the norm of v sub j. However, v sub j is not the zero vector, so its norm is non-zero, thereby showing that the scalar a sub j must be zero. But this actually shows that if we have an expression involving the zero vector, each of the scalars a sub j must be zero, so there must be no non-trivial expressions of the zero vector. Hence, our set S prime must be a linearly independent set. Now, we'd like to show that we actually do have our expression involving the linear combination of any vector y as an explicit formula. So let's say that y is in S, in W. Since W is spanned by our set S, we know that y here has a linear combination of our vectors v sub I. We'd actually like to find the formula for our scalars a sub j. The way that we'll do this is take this expression for y, and I'll take the inner product with any vector v sub j. We'll then find that the inner product of y with v sub j must be equal to the scalar a sub j times the inner product of vj with itself. This thereby allows us to solve for a sub j, so we find the formula as in the original proposition. As a special case, when we have an orthonormal basis, then the norms of our vectors u sub I are 1, and the formulas for a sub j are slightly simpler. Thanks very much for watching.